Hello and welcome again to my Physical Science Online Lab video supplement series. Today's video is a lab walkthrough video on the spring scale lab, um, and this is going to follow through this building a spring scale lab handout that I have made for this lab, along with a few sample calculations and also actually a little bit of thoughts on where you can go to get the spring needed to make this lab work. Because I know that of all the labs that we do, this lab where we have to use a spring is the one where people most often start sending me emails, where can I get a spring? How do I find a spring? Where can I find a spring? What spring should I use? That kind of thing. So I'd like to cover that in this video as well, and a little bit of what the experiment looks like, a little bit of what the calculations look like, and so on. Okay, so first up, there is a little simulation activity in here that you can do in addition to this lab, showing how to build a balance scale, and this is from University of Colorado's PhET program. And there's actually a second simulation that you can find from these guys that involves building a spring scale. Basically, how does a spring, how much force is applied to a spring, and therefore how much force is applied by the spring, that's a Newton's third law pair, as a function of how much it's stretched. Okay, or compressed if you have a compressible spring, but we're focusing here on just stretching the spring. Okay, so first things first, what equipment are you going to need? This list is a little bit more drawn out than my usual list. Instead of just listing each item, I have listed them, but then I've also maybe added a few comments with where are some suppliers for some of the ones that might be harder to find, like a set of masses and a simple spring. Okay, first thing you actually need is some sort of measuring device. So a meter stick or a yardstick or a tape measure. I have a little ruler here. This would work. This is actually called a nano stick. It's not exactly a ruler, but a ruler. As it turns out, the scale that I have, the little spring holder that I have for my own setup, has a built-in scale. Something like that. Something that can give you lengths in preferably centimeters, but if you can only get it in inches, then that's fine. You can always use the conversion factor that was provided in a previous lab, which is that 1 inch is 2.54 centimeters, and then of course 1 centimeter is 0.01 meters. All right. So you need something to measure lengths with. That's your first item. Second item, and this is the one that everybody starts saying, okay, where can I get that? That would be a spring. And what I'm going to do here is I'll just kind of show you some of the places where you could look around to try to find a spring that'll work for this lab. Okay. So Pasco Scientific is one of the major suppliers out there for education in science. This is a spring set, demonstration spring set. This would work. This is maybe a little more pricey than a lot of you are going to want to spend, but you could try searching on their website for like a Hooke's Law spring, or like spring and Hooke's Law, something like that. The nice thing about these guys is that they tell you these information up front. So you know that you're getting spring constants of 3.4 newtons per meter or 6.8 newtons per meter. And it turns out that that basically is telling you something about the data that you're going to be collecting. So you have like a double check. It turns out that this is the spring force constant is what you're ultimately measuring in the lab, and so you have like a nominal value. But of course, you're paying a little more for these products than some of the others that I can show you. Some other places you could try going. You've got Fisher Scientific. Fisher Scientific has the ISCO Hooke's Law spring set, $6.87. You know, much cheaper. They should have, I think, possibly like a set of 3 springs on here somewhere. I guess maybe not. But like this right here should work just fine, and obviously is a lot cheaper. I will say that the odds are that these are going to be a bit looser. Um, and then the descriptions that are given for the springs are down here. I'm thinking, um, so it's telling you what is the spring constant, but it's giving it to you in different units than what you're supposed to be converting to. It's giving you in grams per centimeter instead of newtons per meter. And it's also telling you, and this is important, how much maximum mass can you hang from the spring. Okay, and we can come back to that point later. But basically, what it comes down to is all springs have what's called an elastic limit. And if you put more mass than whatever that elastic limit is, then they cease behaving as a linear elastic device. So like here's a spring. If I hang weight on it or if I pull on it, it stretches out. And then if I release, it goes back to its sort of equilibrium or unstretched length. Well, it turns out that if you stretch this too far, for example, by putting too much weight on it, then when you release it, instead of snapping back to this, maybe it snaps back to something like this. All right. So it won't return all the way to its unstretched length. It still may function fine as a spring, but among other things, you're sort of going through this whole process to calibrate a scale. And if you exceed the elastic limit, when you remove the weight and it returns to not its original length, then it may not actually be functioning with the same spring constant as it had before. And so your calibration is kind of invalid. So knowing what these maximum weights are is important for that. There's also this spring set from Vernier. These ones are 6 centimeters long. That's a little more than 2 inches. And they're basically, you have 6 of them. Like it's a set of 6. So like if you happen to be taking this class online, but you know a few other people in the class and you want to go in on springs together, then like if there's 3 of you or something, you could buy one set of this and then you each have 2 springs at essentially like $6 each. Okay, and so then maybe you'd pick one of the stiffer ones at 15 newtons per meter, one of the less stiff ones at 5 newtons per meter. This one doesn't really show you right here what the maximum amount of force is that you can apply. It may be in the frequently asked questions, and that's fine. Kind of a rule of thumb that may work out. Your mileage may vary, but I found with these springs that if they are like 2 inches long, you can stretch them out to somewhere around 8 inches and they'll snap back just fine. So you can stretch them to like 3 or 4 times their unstretched length and they'll be okay. But if you go much more than that, then you're going to start risking having them not return. Like you might be able to get 5 times as much out of them or something like that. But if you if you go out to like 7 or 8 or 10 times the unstretched length, odds are pretty good it's not returning to its original condition. Okay, so last place that you could try looking for a spring, maybe the most convenient, is Amazon. And this one that I've pulled up here, like I already showed you some ISCO springs from Fisher. You can see that they're actually cheaper from Fisher, although I don't know what the shipping is. I bought this set for doing this video and for doing this experiment. So this set that I've got pulled up right now, the ISCO Labs Hooks Law Spring Set, is the set that I have used. I will say that for these 3 springs, basically it comes as in the picture, 3 springs, 3 different spring constants, 2 that are kind of longer and 1 that's kind of shorter in length. And you can actually see, if you're looking closely, that this one that's shorter in length is not as much shorter as shown in the picture. And the reason for that is that I actually did, in a different experiment, exceed the elastic limit of this spring. Turns out that this shorter one, the elastic limit is somewhere in the neighborhood of 80 grams for what that's worth. So if you buy this set and you decide to use this smallest one, don't put like 80 grams on it. Try to stay maybe 70 or below. The other 2 you'll actually need to put more than 80 on, and I didn't go to the elastic limit on them, so I don't know what the upper limit is, but as long as you don't stretch it out by more than like 4 times the original length, you'll be okay. There are obviously like a lot of other springs on here at a lot of different prices. I would recommend either doing this ISCO 2-inch spring set, which by the way you'll notice the price on Amazon $10.49, from Fisher $6.87. So if budget's a concern, maybe find out what the shipping costs are. But I'd either do like this ISCO Labs one or this one here, which is the one for this very video, or go to Fisher or Vernier or Pasco would all be fine. Maybe Carolina Biological may have one. Certainly they have these spring scales. These are fine for something else. Like you can use this to double check your experiment, but don't just buy a spring scale and say, here, I have a spring scale, and so I've done the experiment. So you're basically making one of these spring scales in this experiment, but don't just go buying one. Okay, and this in the handout is actually a link to the one on Amazon that I was showing you. Okay, third piece of equipment, you need a set of masses. Okay, so there's quite a bit of stuff you can do here. In the previous iteration of this lab, so this is an updated version of a lab that I was doing the first few years that I taught this course. In the previous iteration, I had people getting a more robust spring, and instead of using a weight set, I had them using water. And so you'd have like a cup and you'd add some water to it, and then based on how much water you've added, you know how much weight you've added. But that was kind of ending up being more of a hassle than it was worth. So part of why I've updated this lab is because I think it's just easier for you to go buy one of these easy springs and then get a weight set that works with it. So what can you do for a weight set? Well, you can use a fishing sinker. You can go find some slotted weight sets. And in fact, again, if I pull up my Amazon searches or Fisher or whatever, like these guys have like a slotted weight set. Amazon, you can go look up slotted weight sets. Like this right here is a nice slotted weight set, $22. There's cheaper slotted weight set like this one for 12 bucks. I think I found one that was even cheaper. Maybe not cheaper, but like also works out okay. These are 10 grams each. They come with a hanger. They're it'll work, and you can get something like this from either Amazon or Fisher or Pasco or Vernier. All these scientific suppliers will have them. Um, Another option, so before the other option, what's nice about the slotted weight set is they tell you how much mass everything is. If you're looking at this thing on screen, um, so go here. Hello. It says here on the screen that it's a 10 gram mass, and like each one of these is another 10 grams. So you know how much mass you've added without needing any other apparatus. So that part's kind of nice, but you are also sort of like paying for this product as a result. Okay. Other option besides that, that would maybe have a standard weight to it, is something like these fishing sinkers. So a lot of people, especially here in the South, but all over the place, a lot of people will go fishing anyway, and so you may have some of this at home. And if that's the case, then maybe use these. The main thing is you have to know how much mass each of your little sinkers has. So like this one right here, actually when you buy it, it tells you this is how much in ounces each of the sinkers could be. All right, and so you'd basically go through and say, all right, I want my 1 ounce 12 pack, or maybe I want my 3/8 ounce 24 pack, like $7 to buy this. So it's cheaper than the other thing. You would want to go look up a conversion factor from ounces to grams so that you have this mass in grams. Okay, other options, you can buy like an actual weight set that has weights like these in it, but that tends to be more expensive. What I actually ended up doing, and this is probably the cheapest option, um, is depending on what gas prices do, is the cheapest option. I went to the hardware store and I just bought some little washers. So you can use like a bolt or a washer, maybe not a bolt, but like a nut or a washer would work pretty good. And then if you do that, you will probably want some way to attach these to your spring. And so in the event that you do like washers or nuts or fishing sinkers, something that doesn't have a hanger with it, you're going to want like a piece of string of some sort. This actually is some relatively heavy fishing line, but just plain fishing line should probably work fine for this. I've also heard of people using like dental floss or like a kite string, or even like if you do sewing, maybe like the thread would probably work for the weights that we're going to be using. Okay. And then the last thing that you need, and this is, I say optional on here, it's what it comes down to is you need to know how much weight each of your weights that you're using is. So if you bought a mass set and it tells you this is 10 grams, then you can assume it's 10 grams. If you bought a fishing sinker and the fishing sinker says on it, this is 3/8 of an ounce, you can probably assume it's 3/8 of an ounce. All right. But if you ran to the hardware store and you bought washers like this, these are nice and cheap, and you can get enough of them to do this experiment, certainly with those ISCO springs that I was showing. But you don't necessarily know what the mass of one of these is. So you got to have some way to get the mass. One way to do it is to use some sort of a balance scale. And some of you may already have one of those at home, like if you do like chef type stuff, you cook and you want very finely measured amounts of ingredients. But If not, if you don't have one and you want to order one, I have this little scale here. This is what's called a pocket scale. It's this size. It literally fits in your pocket. This one right here actually came from Carolina Biological, which I guess is now both Carolina Biological and maybe has a subsidiary Carolina Distance Learning or something like that. But these are basically their little pocket scales. They're running like $15 or $17. Probably you could come to Amazon and just search like pocket scale, something like that, or digital pocket scale, and it'd probably come up with something similar. Um, okay, so this one like 15, $16. Here's one for $10. Okay, so you know, depending on what you want to fork out for it, maybe you can get one for even like $9 or $8, something like that. So that's what you will need if you are just using some washers. So you pick how you want to go about doing this. The other option, of course, besides buying a pocket scale, would be to build your own balance scale for these if you have these. And for that, you basically need some object of known weight and then a stick that you can balance one of these with that known object, and then that lets you calibrate how much this weighs. But I think it's probably easier for you to just either have one of these digital scales or buy a standard weight set. All right, so I think that's all I need for products for the day. So now what are we doing in this experiment? Basically what you're doing is you're trying to balance or set up a spring balance scale. And what I'm going to do here is I'm going to first of all just show some of the basic setup for it by first of all I'm going to move the camera so that it's at a more advantageous angle for showing the experiment. Again, what you should see here is the little stand that I have set up for hanging the spring from it, and then I can attach one of the springs to this stand. I think I'll use the small spring from IceCo, knowing of course that it's changed since I had hung too much weight on it previously. And then down here I have my little digital scale, and what I have to do is I need to basically place my calibration weight on it. Maybe turn it on first. Okay, so it's on, and then I place on it my calibration weight, and then I can read off what is the mass. Okay, and so this says there's a little G here for grams. It says 6.9. So this much weight is 6.9 grams. And so what you would probably want to do here, and what I'm going to do here, is I have previously done this experiment. You can see my data and everything for it for all three springs. But what I'm going to do is I'm going to go ahead and sort of like redo the experiment, but for one of these springs. Maybe I'll use the small one because it's already ruined, and so the values may be different than the correct value. And so you're going to get a different result probably than what I'm getting here. So all right, we've masked this. We now want to point this guy towards the spring so you can see it. Here's my spring. And then what I've done is I take the string, and if you want to be really thorough, you can mask the string on the scale along with the little washer. It turns out that this brings my total to 7 grams rather than 6.9. Okay, so then I take the washer like so. Maybe I take the spring off to for working with it, and then I thread it on like so, and then thread it on like so. Okay, so before I go hanging all this stuff on here, I need to measure what the unstretched length of this spring is, and according to this, the unstretched length is about about 5.1 centimeters. Okay, so we put on here in our little data table that I'm going to be making, let's say ISCO spring short. Parenthetically, it's the, I'll call it the ruined one. It's not really ruined, but like it's been overstretched. And then unstretched length, and we'll say that this, I said, was 5.1, and that's in centimeters. All right. So what I would do from here basically is I need to move my scale up here as high as I can get it to go so that it's measuring the actual length now of the spring. Okay, and it turns out that I have already stretched this spring, whoa there, by a couple centimeters. Like this length is now 7.5. So in some sense this is longer than what I told you to stretch with each increment of weight. Okay, so if you were doing this at home, you happen to have bought the ISCO set, you happen to have bought some 7-gram washers. Each one washer is more than enough to stretch it. These actually stretch on their own, just under their own weight. So in here, there's a statement about not all springs immediately begin to stretch when weight is added to them or when mass is added to them. This set actually does begin to stretch pretty much immediately, but some of them are coiled tightly enough that you have to start adding weights. So for this set, where it says like W0 equals, I would just enter like 0 here. Okay, so back to entering my data. So unstretched length is this. What I'm going to do is I'm going to do increments, let's say mass in grams, let's say length in centimeters, and then we can do weight or force, say force in newtons, and stretch in meters. Let's do stretch in meters first. Stretch in meters, force in newtons. Okay, so increments, the instructions tell us that we want to add 6 to 8 values for this. All right, so coming back over here, 6 to 8, let's just pick a middle value in here. We'll do like 7 increments. First amount of mass that I added was 7 grams. So we'll say 7.0. And the length is about 7.5. Okay. Now, what we can do for these two is make them calculated columns. So you see that I'm entering a calculated value here. Let's hold up. So I've started by entering an equals sign, and then basically what I can do is click on this length here. Maybe I should put a parenthesis first. Click on the length, subtract the unstretched length, And then I'm converting from meters to centimeters, so I've got to divide by 100. And because I'm going to be repeating this over and over again, I'm putting a $sign between the letter and number for the cell. What that $sign does is it basically means if I select the next cell down and repeat, then this one without the $sign will also increment down, so it'll say D11 instead of D10, but this will remain C6, so it will continue to use this unstretched length. Okay, and then for force, basically I should use my mass times 9.8 divided by 1,000. So my mass in grams divided by 1,000 gets me my mass in kilograms. That times 9.8 gets me my weight in newtons. All right, and what I'm going to do is I'm going to highlight these two cells, and I'm going to highlight all the way down to the bottom of the table that I'm making, and then basically fill down by essentially like Control D on my computer, or if you grab this thing and pull down, we'll also do that. And these numbers will update as I add more masses and more stretches. Now, one thing that you can do if you'd rather not have to deal with measuring the unstretched length each time is you can, instead of measuring an unstretched length and then measuring a total length each time, you can also make this one effectively 0 by moving your scale so that when there's nothing attached to it, you basically move your scale up and down so that the 0 on the scale is aligned with the bottom of the spring. Okay, so in some sense what that has done is it's made it so that I have a 0 effective length when there's nothing attached. Okay, and so then when I add this string, let's see, this little hook on the scale is a little weird to work with. I add the string and the mass to it. It's stretched out. Let's see if we can zoom in a little bit. So we're stretched out, and basically I would just look at this and line it up on this scale and see what number it happens to be lined up with, and that's what number I would then want to enter for my length, and then my stretch will just be the same thing as my length by doing it this way. Okay, so gotta turn it around so that I can actually read it. Looks like about 3 as it turns out. So call it 3.5. Okay. Then we want to add our next increment of weight. So you can basically pre-weigh these in advance if you'd like, and then you'll already know, like, okay, I'm adding, maybe they all have the same mass, so I'm adding another 6.9 to it. Remember, the string is 1 gram, and each of these seems to be about 6.9 grams. So take it off, add on another one of these washers, that's another 6.9 grams. So over here I'd go 13.9, and now I have a length of about 7. Okay, and then I add another one of these guys. Whoops. So you get a third one of these guys. It's again going to be stretching a little more. What I'll do is I'll measure this one, and then I'll pause the video, make my measurements, because they're all the same measurements over and over and over again at this point. And I'll just fill in the rest of the data table and then turn it on so that you know like what to do next. Okay, So this one happens to come down to 10.5. So we're at this plus another 6.9, and this is 10.5. All right, so I've finished taking the data at this point, and this one is stretched actually below the plane of the table at this point with 7 of these on here. But I've measured it using my sort of ruler here, and I've written in the values that I got at each step along the way. So now I can take this thing off, and then basically go on to the rest of the calculations part of this lab. So let's pull this back up. Nobody wants to look at a blank table. Maybe nobody wants to look at me either, but there it is. So here we have our instructions for what to measure. You're supposed to be making some sort of a graph which has the amount that the spring stretches on the x-axis and the weight on the y-axis. Okay, you're supposed to linearize the graph and then analyze it a little bit. In this particular program I'm using, this is LibreOffice. Basically, to make a graph, what you do is you go Insert Chart, and then it pops up a little dialog menu saying what kind of chart do you want to insert. And so you tell it, and you should always tell it scatter plot, just a basic points only scatter plot. Excel, if you're using that, will have a very similar interface. Again, you'd maybe tell it to insert a scatter plot chart from the get-go. Okay. Once you've told it what kind you want, you hit next. Then in my case, we hit next again for data series. I'm just going to add one series because I've done it for this one spring. And then essentially what I do is I just select the ranges for stuff. So first of all, I give it a name. If you're going to do this for 2 or 3 springs, you should probably name each set because you're going to want a key. My x values, it said to use the amount of stretch in meters, so I select this column. I've just highlighted those. For the y values, I need the amount of force in newtons, so I highlight that column. Okay, and then you should always want to put on it like a title of some sort. So you could do like, you could call it like Hooke's Law for an ISCO spring or something like that. And then on the x-axis, or you could call it like calibrating a spring scale, maybe use the subtitle, something like that. So calibrating a spring force scale. Okay, x-axis, again, we put the stretch on that axis in meters. On the y-axis, we put the force in newtons. So we type all that in. We hit finish, and now it has force versus stretch. You can see what the essentially what the graph looks like. You can also see that it's not a perfectly straight line. I actually have a typo here though. This should be 21.9. It's still not a perfectly straight line, but it is obvious that if I was going to draw a line through it, that the line would fit it pretty well. So on Excel, to do that, you basically click on the data. I'm on a PC, so you right click on the data and then put insert trend line. So you have insert trend line, I like to show the equation on the graph. I also kind of like to extrapolate backwards so that the line goes back to my x-axis. So my initial is 0.035 here. So to go backward, I would just need to put in like 0.035, something like that, and it should extend all the way back. I get an equation that is kind of lengthy here. For my own sanity, what I do is I usually click on it, format it, tell it that it's going to be a number, and make it have like one or two decimal places. When you do that, you get an equation of fit for this chart. And if you want, you can do other things like making it pretty. You could put like the grid in it if you want. Whoops. Hello. So you could do like major grid, and now you've got a major grid on there. If you're graphing this by hand, for example, you'd want to use graph paper, and you'd have to find the slope of this line by hand. If your line happens to not be a line, if it's nonlinear, then you may have to make a second graph to linearize it. But this is basically it. Like now we have the graph, we have an equation of fit. This happens to be linear. We go into our instructions and read what else it says. There's a little caution statement about not stretching the spring out too much. Whoops, didn't mean to do that. So what kind of graph did I obtain? Well, this looks very much like a straight line to me. You may or may not also get a straight line. Okay. If it's a parabola, you got to linearize it. So how would you go about doing that? Well, basically, like if these were parabolic, you'd add another column here where maybe you like squared all of the length values and then regraphed it force versus length squared, and that could turn it into a line, or maybe force squared versus length, that could turn it into a line if it's a parabola, etc. Okay, this asks what the units are for slope. All right, it's not obvious from the equation of fit what the units are, and you're also supposed to write an expression to get the spring constant, or to get the total weight from the initial weight, the stretch, and the spring constant. Okay, so we pull up this thing again. This is basically the form of the equation. F of x is basically whatever is on this axis, which in this case is force, which is weight. X is whatever's on this axis, which is stretch, which in the equation we're writing is x's. This slope represents your spring constant k. This intercept would represent your sort of internal tension, how much weight is needed to add before it starts stretching. Notice that I got an intercept of basically 0. If I took it out another digit, I think there'd be something here in this hundredths place, but we can count this as more or less 0, especially given that my smallest mass is well over enough to make it begin stretching. Okay, so if I was writing this equation in the form here, I would basically be writing out, let's write it out here. Okay, so I have this graph. Let's copy it into here. Just paste it here and put it like right here. So then basically what I would do is I'd say, okay, I'm trying to get an equation of the form total weight is equal to some function which has in it stretch, spring constant, and internal weight. All right. Well, the internal weight is this guy right here. The spring constant is this guy right here. And x just happens to already be in there as x is right here. Okay. So you're going to want to basically write this equation, but with x, k, and w naught. Okay, so also asked was, what are the units of slope? All right, and for that, we need to look at what's here on the x-axis and what's here on the y-axis. And specifically, we need the part in parentheses because those are the units. So slope for a straight line is given by the rise over the run for the line. And so that is delta y over delta x. In other words, whatever's on the y-axis over whatever's on the x-axis. So in our system, that would represent a change in force, which has units of newtons, divided by a change of stretch, which has units in meters. Okay, so slope units are newtons per meter, and these are units for spring force constant, or sometimes just called spring constant. So spring force constant. All right, and then let's look at this again. So we've kind of done everything in here at this point. Then also there's like this question, what if you take an object that has an unknown weight on it and you hang it from your spring? And so then the spring is going to stretch some distance. And can we figure out what the object's weight is and therefore how much its mass is? All right, well, I don't really have a good unknown object here, but if I point this again at this guy and I take my spring once again, put it on here, I do have a little mass from one of my mass sets that I can hang on to this spring and it should stretch some amount. All right. And so now I should be able to look on here and measure how much has it stretched. Whoa, Nelly. All right, so it's down at the basically 5 centimeter mark. Okay. So what do I have here? Let's do, oops, that's not what I wanted at all. Okay, so let's do unknown mass. Spring stretched 5.0 centimeters. All right. So we've got 5.0 centimeters worth of stretch. We know that the weight total is, in the context of my system, 1.9 newtons per meter times x plus the internal weight. And again, in my system, the internal weight is 0. So x would be this 5.0 centimeters, but since this is in meters, I need to make this in meters as well. So this is 0.05 meters. So my total weight is 1.9 newtons per meter times 0.050 meters. And just want to do a quick double check of the stretch. I eyeballed it wrong. This is more like 5.1 centimeters. So scratch this off and put 5.1. Scratch this off, put 5.1. sometimes doing stuff in haste doesn't get you the best of all results. So to do this, I need to get out a calculator, and obviously I have the calculator on my computer that I can use. Maybe. Here we go. Okay, so I have 1.9 newtons per meter times 0.051 meters. And so according to this, I have a total weight of 0.0969 newtons. 0.0969 newtons. And again, probably realistically should round this to 0.097 newtons. There's no way that I'm actually measuring precisely enough to retain this digit of precision. All right, and then to get the mass, remember that weight is mass times gravitational field strength. So that means that the mass, m, is the weight W over the gravity field strength G. So this is 0.097 newtons, and then divided by 9.80 newtons per kilogram. And so my weight, if I open this calculator again, I can divide by 9.8. And what I get for my mass, oops, I've put weight here. I should be putting mass here. M is 0.009, what did this say? 9887. So 0.0099 kilograms. That's the same thing as 9.9 grams. Okay, and just to be clear, I'll label this is my mass right here. This is my weight right here. Even though I've stated it orally, like I've stated this verbally, out loud, whatever you want to say, I should maybe write it down just as a reminder. This is mass, this is weight. Okay, and what did I actually hang from it? I don't know if it's readable on my camera or not, but this is a 10-gram mass set. So to within about 1-ish% accuracy, I got the right mass here. And more precision would basically require a finer scale here of some sort. Okay, so I think that covers everything that you really have to do in these instructions for this lab. Now, bear in mind, of course, that when taking the quizzes for these labs, obviously, I can't write a quiz that just simply asks you the exact same stuff that you did in lab and have it all worded the same, because Canvas has little internal eccentricities. Blackboard has internal eccentricities. Any online system is going to have some internal eccentricities to it that just can't be nicely translated from these instructions to a quiz. So, expect to be asked some questions like, what kind of graph did you get? Maybe if you did 2 different springs because you ordered one of the sets I got, you could answer the question, is the larger spring constant stiffer or less stiff? And by the way, I would recommend you do this for more than one of the springs if you do buy yourself a kit. And even if you end up buying a set that has like 2 identical springs, one thing that you can do in order to give yourself 2 springs instead of just one is you can take the springs and basically just attach them end to end like this. So this is called a series connection between two springs. And if you do that, you'll get a different spring constant than you would have for either spring taken alone. All right, and so that lets you practice this on more than one spring type. And I would definitely recommend that you do that. Okay, so I think that covers everything in our instructions. Uh, quiz question wise, yeah, is a stiffer spring um, higher or lower spring constant? Could be a valid question. What kind of graph did you get? What does the slope tell you? What does the intercept tell you? Convert from so much weight to so much um, or so much force to so much stretch, and vice versa. Given a spring that does not have immediate stretching under its own weight, so like these ones pretty much immediate stretching under their own weight, but like if I have a spring where I have to hang a few weights from before it stretches, so this one right here is from my same kit, and if I hang one of these guys on it, does it stretch immediately? And I think that for this one, the answer actually may be no. It may not stretch immediately. So here is it unstretched with the thing hanging on it. There's not an obvious stretch to it with just one. Maybe like a very small amount, maybe not. So depending upon, if you're doing this at home and you happen to pick a washer set that has a smaller washer in it, then this one may not actually stretch immediately. So given that, I would definitely expect you to be able to, write the equation out, but also being told if I hang, say, like 40 grams from it, how much stretch do I expect it to have? If I hang some unknown weight from it and it stretches by 10 centimeters or something like this, how much weight did I hang from it? Those are all valid question types for this quiz. All right, so I think that does it for me today. Hopefully this video is helpful to all of you in doing this experiment, and good luck.